The next section about optimization is called evolutionary algorithms. And this actually follows on from neural networks in an interesting way. Sometimes if you're using gradient descent, frankly, it just won't work. Maybe the parameter space is too large for the compute resources you have. Maybe specifying an objective function, maybe you can't even get there. Maybe the problem is so new or so complex that you can't come up with a function to apply something like gradient descent. Perhaps the best approach is for the machines to consider a set of reasonably good candidate solutions, maybe not the ideal ones, but good starting points. Be able to essentially evolve those, a set of good starting points, and then provide that to experts, domain experts, to go back from first principles and be able to come up with a good solution. So an area that's coming around is called evolutionary algorithms. You may have heard of genetic algorithms, or a subclass of that very important called genetic programming. And essentially they use search heuristics within your set of variables that mimics natural selection in biology. So you're representing the problem in terms of genes, if you will, and you've got a population of candidate solutions, and you take and breed them, exchange their genes, and then evaluate which ones get you closer to having a good solution. And you just go through many, many, many different generations, breeding up a population until you get better and better candidate solutions. Actually, before I go into the example, probably one of the more interesting cases of this was in the sense of designing antennas for spacecraft. So if you've got deep space missions, some type of space probe that's being sent out, how do you create an antenna for that kind of use case? And one of the things that evolutionary algorithms showed was, if you look actually at the Wikipedia page for this, they've got a good note about it. You might think of an antenna, you've got your little box and, okay, so we've got some antenna. That's kind of abstracted, but if you're going to put a really good antenna on a deep space probe, how do you design it? It turns out that the engineers are having troubles with this, but they built up a representation in evolutionary algorithms to be able to evolve candidate solutions. And it turned out that there's this wacky kind of antenna that looks like this. And that ended up being a very non-intuitive solution, but also quite ideal. So I want to emphasize the point that evolutionary algorithms are really good at coming up with candidates. They may not be what you end up using in production, but it's sort of thinking out of the box for the experts. And we've seen this time and again in use cases where you don't have a simple problem. You can't just use gradient descent. And so by definition, you probably do need to have your experts thinking out of the box. It might take a design cycle of, say, 18 months to solve a problem with traditional methods, but you can bring in evolutionary algorithms to cut that 18 months down to maybe 3 months by just accelerating getting good candidate solutions in front of the experts. So there's Python examples. There's a distributed system called Exelixi for evolutionary software. I'm one of the main authors on that. Came out last year, and we're showing how to do genetic algorithms and genetic programming. There are some examples there. They're a little bit longer than our 50 lines of Python limit that we had here, and they're probably best to just look at the wiki itself. But there's an article entitled Zen and the Art of Bicycle Route Planning, and it takes a hypothetical teenage Steve Jobs riding his bicycle, running around doing his weekend chores. I actually live on the block that Steve Jobs grew up on in Mountain View. So let's see here. We've got a genetic algorithm that defines young Steve going and doing some grocery shopping and buying some crickets for his gecko and I don't know, getting a haircut or something. Genetic algorithm basically is representing a cost table for this routing problem. And we're basically evolving different candidate solutions. We're evolving a population of them. And then we take the best ones at the end of every generation and breed them together. Basically, find a split point and merge the respective genes from either side, from either parent. And then evaluate the cost. Get rid of the ones that don't end up having good solutions. So here's running through this genetic algorithm, doing a routing problem. It goes through, what, 23 generations, and it comes out with routes down here. You see one that has pretty good value on it. And what that turns out to be is, if you represent it in a map, here's young Steve Jobs at his home in Mountain View, and here he is going off, to the grocery store or returning a copy of a Ram Dass book to the library, etc., over in Mountain View. But again, it's working with an optimization problem. You can kind of see the fitness going on here, but it's the kind of thing that you cannot easily represent in terms of, like I say, gradient descent. It's a much more complex problem. There's another one, an example here that's genetic programming, where we actually evolve a program, a set of codes, to run on some hypothetical machine. In this case, it happens to be for how to route drones around a city square. A couple vignettes here. I want to show one about John Holland, and he's credited with many of the advances in evolutionary algorithms. An interesting thing, back in 1963, he came out with a report when he was at Michigan. He was tasked with developing a test plan, doing QA for an IBM mainframe, a 701. And what he proposed was something called machine adaptive systems. What he wanted to do was evolve the test plan and use neural networks, but he had to evolve the neurons. So this is interesting because this is where it sort of crosses over from what McCullough and Pitts have been doing not so many years earlier in terms of neural networks. And now we've got this idea that we want to try to evolve populations of neural networks to try to solve a really complex problem, a QA plan. So you can see down here what Holland's drawings about how he's cutting down the search space. Basically, it's a very nonlinear problem, but you can get out to these candidate solutions for how to find the right kind of test vectors. Very interesting thing. Rolling the clock up to now, there's a researcher, Claire Legouze, out of CMU, a professor there, who had a recent paper entitled GenProg, a genetic method for automatic software repair. And the big idea there was that Claire Legouze and her team had taken the commit histories on GitHub for a lot of popular open source packages, taking a look at how they were fixing bugs or patching security problems. And they applied genetic programming so that they could evolve more patches for other open source projects. And it's great because some of these have like $1,000 bounties if you can solve a security problem on an open source project that's popular. She found that she could use genetic programming to knock them down for about, I think it was like $5 each. So, okay, great. We've got some machine learning that's going to start rewriting our code. I think that's actually kind of a good thing. Some popular books on the subject. A Field Guide to Genetic Programming is a really great one. There's a free download. Back at Ann Arbor, where John Holland spent most of his career, there's a conference called Genetic Programming in Theory and Practice, Rick Riolo and Bill Rosal. And also John Holland's book, Hidden Order, is also a very good one.